Axel vous fait la présentation en anglais. Over to you, Axel.
Merci bien, merci bien. Merci bon pour les, comme diraient les Américains, very, very kind words. La présentation sera en anglais tout simplement parce qu'en fait, je fais toute ma recherche en anglais vu que la recherche doit être présentée ouais, dans des forums internationaux, mais les questions naturellement peuvent être en français, en anglais, en allemand, comme vous voulez. Ah, ok. Bon, d'accord, il faut que je trouve ma présentation là. Et puis
Ah oui, oui.
pas de problème, pas de problème.
Je le retrouverai. Bah oui, j'ai compris.
C'est bon.
Ok, super.
Ok, super. I will switch to English now. All right, topic today is fact-checking, computing the veracity of knowledge graphs. You've heard about knowledge graphs the whole day, so I'm not going to spend too much time talking about what knowledge graphs are. What I'm really going to be interested in is talking about why it is important to actually know whether the data you have in your knowledge graph is correct, i.e., whether it represents the reality in which we live at the moment. So let's begin. I think I basically always start with a disclaimer. Sorry, I have to make sure I figure out manipulate this. We're good. So I always start with a disclaimer. I am not going to talk about everything that is available with respect to knowledge graphs. That would make little sense and would take way too much time. So this presentation is going to be very incomplete. I am going to focus on particular methods pertaining to fact checking and fact validation on knowledge graphs. I am not going to talk about fake news detection. This is a different topic which demands other types of methods. However, there is obviously an interface between fake news detection and fact checking in the sense of knowledge graphs, because basically we're looking at the same data just from different perspectives. And I'm also not going to talk about knowledge graph completion, which is basically very similar to fact checking, but it's done in with the perspective of the whole graph. What we are going to be interested in is not the whole graph, it's basically taking a particular fact in the graph and asking the question, is this fact true or not? That basically, I hope, situates what we're going to work on. But we'll start with this one. And basically, Trump used to make my life so easy because I would simply have to catch the new statistics on the false or misleading claims that he made, and that would be sufficient to motivate why it's so important to have true knowledge graphs. He's still the president of the state, so I can still use this slide. Next year, I'll have to think about something else. But basically, on July 9th, 2020, Trump hit basically what is considered a milestone in the history of presidencies, let's say of US presidencies. And that was the milestone of hitting 20,000 false or misleading claims in his statements. And you can imagine that if you were to build your economy on such claims, you would obviously crash once the claims are shown to be untrue. That same holds really for knowledge graphs. If you imagine that you have queries, which depends on facts in the knowledge graphs, the more complex your query, actually the more important your query, the more likely it would be that the results you get are incorrect, are simply wrong. It is hence important to know whether your knowledge graph contains correct facts and to know which facts are correct and which facts are not, so that when you query, you can actually also discern as to how likely it is that your results are correct. That is fundamentally why we are interested in the area of fact checking. Journalists use algorithms of the same family on text to be able to produce pictures like this one and to basically be able to say things like, okay, 20,000 facts were incorrect. That's fundamentally what we're interested in doing. We're interested in doing that on knowledge graphs. Now, why is that important? A lot of knowledge graphs that are used in everyday applications, for example, on your phone, if you have an Apple phone, Siri in the back end basically uses a knowledge graph which is derived from Wikipedia. And we know that roughly only 80% of Wikipedia is correct, which basically means that knowledge graphs which are extracted from Wikipedia are also only correct to roughly 80%. There were a few papers which measured that. Gerber et al. Actually got to 77%, if I'm not mistaken. Ruller et al. Actually got to basically the same number. So we know that one fact out of five in a large knowledge graph like the Wikipedia are incorrect. Now, if you go into companies and you ask them how correct is your knowledge graph, if you ask Google even how correct is your knowledge graph, I did ask them, they don't know, which basically means that they don't know whether the queries that they carry out on the knowledge graph actually returns correct results. And that's fundamentally uh, a, a clear motivating example towards making knowledge graphs more truthful, basically increasing the veracity of knowledge graphs. And that's what we want to do with fact checking. Now, there are quite a few different definitions of fact checking. If you look at the works done in journalism, for example, by Graves and Amazin in 2019, they defined fact checking as relating to stories that publicly evaluate the truth of statements from politicians, journalists, and other public figures. So these are the type of guys who basically generate a figure like the Trump figure, which I just showed. That's basically the journalistic definition. If you look at something like Wikipedia, I would say fact-checking is a process of verifying information in non-fictional text in order to determine its veracity and correctness. But the definition that we are going to use is going to be the definition of Gerber and Syed, which basically says fact-checking refers to, number one, evaluating the correctness of and providing evidence for facts found in a knowledge graph. So we're going to have two goals here. Goal one is going to be evaluating the correctness, and goal two here is going to be providing evidence for our fact being actually correct. Main message of the talk, I'll have three main points. And number one is going to be that a little syntax and semantics goes a long way. You are basically going to see that by using a few tricks, we can already do quite a bit pertaining to fact checking. But without those tricks, really, without looking at the ontology of the data, fact checking does not perform as well. So when we talk about knowledge graphs, we also have to think about semantics. That's going to be point one. Point two is going to be that the feature engineering part of fact checking is still an open game. You're going to see that a lot of algorithms are actually run still using manually created features, whilst we now have methods, for example, deep learning, which allow us to learn features directly out of data. It is still unclear how much further this automatic feature engineering, also called representation learning, can actually push fact checking. And number three, we have just begun exploiting embeddings, and I think there's plenty of possibilities there to do tons of research. So if you are interested in doing research, you might want to think about looking into fact checking and into these open questions. And I'll be more than happy, obviously, to support any student who is interested in walking in that direction. Basically, fact checking originally comes from text sources. Some of the key terms which are used in fact checking also come from that region, from that area. That's the reason why we're going to start by asking, how do we do fact checking on text sources in general? There are obviously way more advanced algorithms. I'm going to look especially at the works by Pasternak and Roth, who basically asked the question, which kind of graphical models can I actually use for fact checking? And fundamentally, they came up with this. We have a set S of sources. That's basically the component number one. For example, websites or some documents. And these set of sources assert certain claims. So basically, they say certain facts, and those are the facts that we need to check. So we're going to say each SI belonging to S. Let me use this. So each SI belonging to S asserts a certain claim, and we're going to call the claim CJ, and we're going to say that CJ belongs to C of SI to basically mean that CJ, this particular guy, is one of the claims which is found in the document SI, and obviously CJ is going to talk about particular things, so particular resources, and these resources we're going to call OK. So talk about particular objects of interest. So you have three indices here, SI, CJ, and OK. Now, Once we have that, we know that each claim can be asserted by one or more sources, which basically means that fundamentally, this is the kind of graph that you will expect, right? So you have a set C of all possible claims, i.e. that's the union over all sources of the claims of these sources. And in this particular graphic, if you assume that we have seen everything, this would be your set C. The sources basically are such that they are connected. They can be connected to several claims. Claims can be connected to several sources, and obviously claims can be connected to several objects. But what you see here is that we have a tripartite graph, important from a topological perspective. Now, what are the fundamental assumptions here? Sorry, this takes a little while to get to the next slides. So if you assume that we have conflicting claims, for example, we will assume that Cape Town and Paris are two different cities. And if we say that John was born in Cape Town in the one data set and John was born in Paris in the other data set, these two claims are obviously conflicting because these two cities are not located at the same place, and usually one is born at exactly one place and not several of those, right? So the solution that the basic solution that Pasternak and Rod came up with was to define what they call mutual exclusion sets, M1 to Mn. And basically, mutual exclusion sets are sets such that the elements in these sets exclude each other. So, for example, a mutual exclusion set could contain these two statements. And fundamentally, now once we have the mutual exclusion sets, the question we want to ask is, which of the elements of this set should we prefer over all the other elements, right? So we want to predict the predict the correct claim CI bar for each MI. That's basically fundamentally under this model what we would want to do. And the simplest solution would be simply to vote, right? You remember that we have this graph which gives us the information pertaining to sources and claims and objects and how they're related to each other, the tripartite graph. The simplest solution would basically just be to say, okay, to compute C bar of MI, which is basically CI bar, what we can do is simply count the fact which is claimed by the highest number of sources and say that is the fact that we're going to believe. Obviously, this is a strategy that would have worked for, how do I put this best? If one were basically to assume that the person who screams the loudest is always the correct person, but obviously that is not the case, simply because not all sources are created equal. So some sources will be more reputable than other sources. That's the reason why we introduced the concept of trustworthiness. And we'll say that the trustworthiness, TS, of a source S is the expected confidence by which it asserts claims C of S. Okay, so basically I'm just introducing the terminology here and so that you actually see the big picture. And I see that there are questions. Okay, if there are questions, just put them in the chat. I'll be more than happy to answer them.
No, I think you can take the question at the end, but they can
just... Yeah, sure.
Thanks.
I will. I'm just saying I'll be more than happy to answer the questions. Just shove them in the chat. That'll be great. Okay, cool. All right, trustworthiness, and we'll basically say that a trustworthy source S asserts claim with high confidence. Now, on the other end, though, in the other direction, the confidence of a claim is the trust which is aggregated from the sources which assert C. So basically, if you have high confidence sources, very trustworthy sources, basically they'll assume claims with a high confidence and will compute the confidence of a claim by looking at how trustworthy the sources are. And basically, this is very similar to a problem that we know from information retrieval, right? So if you know the HITS algorithm, which basically looks at sources and says we have hubs and we have authorities, and basically a hub is connected to a lot of authorities and an authority is connected to a lot of hubs, mathematically is really exactly the same problem. It's an eigenvalue problem on a matrix. So we can discover true claims about objects by integrating source, trustworthiness, and confidence of the claim simply by solving the corresponding eigenvalue problem on the corresponding matrix, probabilistic matrix, which we get out of this. So what I'm basically saying is we can build a source claim graph G as follows. What we're going to do here is we are going to say the vertices of the graph are the claims and the sources. And we're going to put an edge between a source and a claim if the claim basically is stated by the particular source. Then we have a bipartite graph. And on that bipartite graph, we can simply run the Hits algorithm to compute the hobbiness and the authority of the nodes. The trustworthiness of sources will be their hub score, and the confidence of the claims will basically be the authority of said claims within the hub and authority definition of the Hits algorithm. That's really the simplest way to do it. I gave you the formal definitions in the slides, and this is basically the equation you will need to iterate until convergence to actually get to those scores. All right, so fundamentally what we're saying here is we can reduce the trustworthiness and the hubbiness problem, or the trustworthiness and confidence problem, to a hub authority problem, and we can use existing algorithms to solve that. You are not forced to use hits. You can use uniform trust or nonlinear confidence or truth finder algorithms and the like. That is basically the same, or it boils down to the same idea. Okay, so we've introduced some of the key terms. Now, how do we do fact checking for knowledge graphs? And how do we build upon what's already there for textual sources to do that? That's fundamentally what we're going to be interested in the next slides. So let's ponder fundamentally what we're given. We're given a knowledge graph G, and we're given a fact T. And the fact T obviously contains, or it consists out of three parts. There's a subject, there's a predicate, there's an object. For example, we can be given the fact that Barack Obama was born in Hawaii. That would basically be a fact. And what we're interested in computing is P of T, where P is the probability. So we're really interested in computing the probability that T is true. Note that I did not tell you, I don't say anything about T being false, and there's a reason for that. I'll talk about that in a second. So there are two main families of solutions to address this problem. One are the text-based solutions, and the way the text-based solutions work is as follows. They basically take this fact, so the fact T, let's say that's our example fact, they basically take this guy, and they try to search for evidence for this fact in large text corpora. And they basically then score the evidence using currently still predefined features. Okay. That basically is directly connected with what I showed you before, because obviously this whole idea of trustworthiness of sources and confidence of claims, that basically plays a key role in the first family of algorithms. The second family of algorithms basically says, okay, you know what, I already have a knowledge graph. So what I'm going to do is I'm going to try to find evidence in the knowledge graph. So graph-based solutions will search for correlated or corroborative paths in G and basically score evidence based on those paths. And we're going to look briefly at both families. So the text-based families, there are quite a few out there, rather prototypical are the approaches presented in the de facto paper in 2015, as well as in the fact check paper in 2018. And this is the kind of architecture that you can expect here. So we are going to assume that we're given a fact, for example, that Albert Einstein, let me just clean this up and make it better. Yeah, so we imagine that we're given this fact, Albert Einstein was awarded the Nobel Prize. You can even have temporal information such as he was awarded the Nobel Prize in 1921. That's the fact we need to check. The first thing that we're going to need to do is, because we want to use text to check this, we need to transform this fact, into natural language. So basically, we are going to need methods which allow us to take triples and to make text out of those triples. You are going to see that very often you're going to need a combination of a bunch of libraries, basically pattern libraries. Pattern libraries are especially useful when you want to transform the predicates. And you are then going to need some labeling functions which allow you to transform the resources. So Albert Einstein Nobel Prize, you will often use simply labeling functions, while for award, which carries most of the semantics really of the fact you are going to need something like a pattern library. You can then get the text, throw into a search engine. The search engine basically addresses an index, and there are two things that you'll be interested in getting out of there. Number one, you'll be interested in getting some form of proof scoring function, which basically tells you, given a particular data source, how much evidence have I found for my fact in the data source. But you're also going to want a trustworthiness score, which I've defined previously, which will basically tell you how trustworthy the evidence is that you found in the textual source. And you will want to combine then those two to return either true or false. True basically meaning that you know that this fact is correct. And if you return true, in general, you will want to also return some evidence for that. Remember that on our definition, we had two parts. One part was we want to know whether the fact is true. And number two, we want to know why the algorithm thinks that the fact is true. So that's basically the area of explainability. If you think about a journalist, for example, using these data, the journalist will be interested in double checking the answer of the algorithm. Okay, so where are the challenges here? The first challenge is actually the generation of the query itself, i.e. taking the fact and transforming that into natural language. So what we need to do to achieve this goal is what we call verbalizing, which means taking structured data like a fact in a knowledge graph, the input triple basically, and transforming that into natural language. And obviously, given that T contains three parts, which are SP and O, this boils down to verbalizing SP and O. So let's look into that in slightly more detail. We are going to assume, for the sake of verbalization, that we're dealing with an RDF knowledge graph, but this really holds for all different types of a knowledge graph that you can find out there. For RDF knowledge graphs, you will see that we really have four main categories of things we can verbalize. We can verbalize what is often called resources or entities. We can verbalize blank notes. We can verbalize predicates, and we can verbalize literals. Verbalizing blank notes doesn't make much sense because these are existential quantifications. If you think about it from the point of view of logics, which means that we are left with having to verbalize E, B, and L. So elements, E being the set of entities, my apologies, E, P, and L. P being the set of properties, E being the set of resources, and L being the set of literals. So that's basically what you see here, entities, predicates, and literals. We basically omit the blank notes because of their semantics. Now, how do we do that? Verbalizing entities, that is relatively straightforward. As I pointed out before, you can use labeling properties. There was a paper by L et al. In 2011, which basically looked into the predicates which are used for labeling things on the web. They figured out that they're basically just a handful, like 20, if I recall correctly, roughly 20. And if you then take your knowledge graph and you basically write a query which retrieves the entries from these 20 predicates, you have found the labels of your resources for most knowledge graphs. What Mendes et al. Also showed is that you can actually use a form of bootstrapping to improve that. You can use links and disambiguation pages on the web, especially on Wikipedia, to actually find even more labels for things. And this picture really gives you an example. So if you find something like an asteroid family, which would be a resource, you will find that in many cases the label of asteroid family in a lot of texts is simply family, and you basically then have to think about which type of scoring functions you should use here to ensure that family, which is rather generic term, is only linked to asteroid family if the context gives you plenty of information pointing towards obviously asteroid family. Am I running out of time? I have an hour, right?
Don't worry. You have
yeah, okay, cool.
And we have time. So.
Okay, cool. Because I'm like, I have so much to tell you guys. It's all very exciting, but it's going to take a little while. All right. So, moving on. What becomes really, really tricky is verbalizing predicate. So, there have been a few works on the subject matter. A lot of the first works, like the works by Marty Hurst, for example, which looked at pattern-based approaches, those works basically said humans are to create the patterns for relations, but that doesn't work because if you look at large companies like Google, they have massive knowledge graphs with thousands and thousands of relations in them. So there's been a lot of work on distance supervision, where the idea is that we look at how a particular predicate is used, we look at textual sources, and we try to basically find verbal clues for particular relations, and that works. That works increasingly better. In the past, it has been used especially for English, and people simply looked at linear structures, so i.e. they considered sentences to be sequences, and they looked for subsequences which matched a particular predicate. But as soon as you look at languages with a slightly more complex morphology, if you consider German, for example, you will see that you actually have to look at phrase structures and look for substructures which are able to basically hint at a particular relation being available. And that's what we've done. We've looked at using a combination of embeddings and so natural language embeddings and phrase structures in 2018 to basically come up with an algorithm which takes something like this, something like Bob was born and raised in Leipzig, Saxony, as well as Alice was born 2018 at Bellevue Hospital in New York City, even i.e. even patterns which contain errors, because in this sentence, obviously, the preposition in is missing. We can still take all of these, generate what we call a dependency path tree. So the dependency path tree is what you see on top here. For people, I guess most people have seen something like this before, but this basically tells you how the different bits of the sentence are related to the main actor of the sentence, which is the verb to be born. And we can then find subtrees which actually express a particular relation. And the interesting thing here, just for the sake of giving you some detail, is that actually we don't really look at born as just a word. We look at born as being a position in a high dimensional vector space, which means that if you had another verb here which were very similar to born, we would still be able to learn on top of it simply by knowing that there are some substructures in that space which fundamentally express the same thing, which is the born relation, right? So we can exploit discrete structures like dependency path trees as well as continuous spaces to actually learn patterns for relations. So that's basically where I wanted to go with this, and we were able to show that this actually generalizes pretty well. Interestingly, though, this was only done in English. So if you're interested in trying this out for other languages, by example, le français, that would be super cool. Let me know. I'll be more than happy to help. All right. What is really tough, and that's actually quite surprising, is the verbalization of literals. And to tell you why, I have this little picture. Now, when you look at this, you're basically going to ask yourself, of course, why does it show this? These are different ways of expressing distances in the English language. So, especially if you think about American English, where they still use the imperial system, you will have units such as inch, stick, hand, foot, shaftments, cubit, length, palm, digit, nail, span, picker, point, line, trip, poppy seed, barley, corns, and so on. They're all basically express the same thing, distances. And they're all related by really weird connections. So, for example, an inch is, let me think, 12 inches is a foot, 2 sticks is an inch, 2 hands is a stick, 3 feet is a hand, oh no, 3 hands is a foot, and so on and so forth. So if you were to see 1 meter somewhere in your knowledge graph, it could be expressed by in 10,000 different ways in text. And basically, you want to find a way which is such that you can still find evidence for something having a length of 1 meter in text, even if it is expressed in different units. And you will see that it's not only for distance, it's for weights, for all kinds of measurements. You have a plethora of possible units, and even worse, people can create their own units in knowledge graphs, which makes the whole thing even more complicated. So here you need a corresponding machinery, which is often very domain specific, which is able to take something like 1 meter and generate the plethora of possible surface forms like 6 inches and 12 sticks and so on and so forth, so as to basically allow you to find evidence for that particular measurement in text. But once you've done that, you can then use a simple trick for query generation. And it is really that once you take the statement, so if we go back to the example which we had, let me fix that. That was ugly. If you take the example that we had, which is Barack Obama birthplace, basically Hawaii, you can now simply take all the surface forms, i.e. all the labels you found for Barack Obama, all the labels you found for birthplace, all the labels you found for his birthplace, which is Hawaii, and basically then generate a bunch of queries in an iterative manner and fire them against the search engine. And once you do that, tadam, so label for birthplace will be born in. You also find that lived in. So a lot of people remain where they were born. So lived in is often a clue for somebody being born somewhere. But it's obviously, if you were to score this, the probability that somebody who lives somewhere was born there will obviously not be 1. It will be very significantly lower. Born in, you will have a very high probability. Move to is actually just an error in extraction. That, so none of those systems is perfect. They all make mistakes. Yeah, and that's something you need to basically take care of in your algorithm then, which computes the scores. Okay, the main question which remains here though, and it's a very interesting research question, is we've used embeddings here, and you can also use embeddings here and there, but there are not that many papers, or I'm not really aware of papers which use embeddings for fact checking when it comes to looking at the entities, especially because usually the entity embeddings come from a knowledge graph, but you're looking in text and you're basically looking at text embeddings, and one needs to glue those two together. But it's a very interesting research question which we are working on, and if people are interested in joining, please do so. That would be great. Okay, so we've covered actually 2 parts already of the architecture we had. We've taken the triple, we've generated labels for the different things, parts of the triple, the SPO, the subjects, the predicates, and the objects. And now we've generated queries. What we really need to do now is actually, once we've spotted things in text, process the text which we've received. So there are a bunch of conditions, for example, that we can set to the things to which we want to, or based on which we want to generate a score. What is often used is something like every evidence sentence must contain at least a verbalization of S, P, and O. So if you look at this particular piece of evidence which was retrieved from text, you will see Barack Obama was an American president. So we have Barack Obama here, served as the 44th president of the United States from 2009 to 2017, member of the Democratic Party. So indirectly we have Barack Obama here, was the first African American president of the United States. Again, we have Barack Obama indirectly here, was born in, that's the predicate, Hawaii, Yipidu. But we still need to create this connection, right? So we still need to connect Barack Obama to he. So what you're going to see is that there's some processing which we basically need to carry out once we found information, and those will include things such as entity resolution, as well as co-reference resolution, where we're basically going to say, okay, we first need to spot things like Barack Obama. We need to say that's directly connected to the Barack Obama. We had a knowledge graph, but we also need to do co-reference resolution to transform the he, which was here before, into Barack Obama again, and basically be able to say, okay, this is really the evidence sentence which we're looking for and which we're going to score further. All right. So once we've gathered the evidence, what we then need to do is do the 2 things I talked about, which was to compute confidence and trustworthiness scores to basically then generate the results of our classifier. And I'm not going to go through all the features that one uses here. There's a bunch of features which people have come up with, which improve the classifiers. But the fact that people are still coming up with features tells us that there are 2 major challenges here that might be quite interesting to work on. And number 1 is basically automated feature engineering. That's still a rather open game for fact checking, and basically exploiting embeddings, of course, because then you could use automatic representation learning for this problem. And I'm basically in the slides, I provide you with a bunch of examples of features which have been used, stuff like pattern features, as well as string similarity counts, as well as token distances and the like. Or it works, but we know that we can do better by basically looking into automatic feature engineering. New. Okay, there are a lot of different families of approaches that one can use to actually compute the trustworthiness. We already talked about page rank and hits. You can use that if you have local data. If you have a search engine like Google search, you will not have access to those pieces of information, but you have access to obviously a very large corpus. And it turns out you can use topic-based measures. I'm not going to go into all the details hereof, but really you can use topic-based measures such as those defined by Nakamura et al. To actually measure how well a particular document actually really matches the topic of the query which you basically generated. And by using these topic similarity scores, you can actually score how trustworthy a document is by basically looking at how likely it really is to be a document pertaining to that topic with respect to a reference knowledge graph such as DBpedia. This is fundamentally the idea here. You measure the topic majority, you say which is the major topic here, how likely is it for a document to have that as a major topic, and how likely is it that that actually matches the topic of my query. All right. Again, for the final classification, you remember we had trustworthiness scores, we had confidence scores, and we needed a final classification. For the final classification, you're also going to need a bunch of features. These are some of the features that were used, but of course, there is a lot of potential here to use automated feature engineering. And yeah, these are the kind of results that you get when you try this. You will see that when combined with different classifiers, basically J48, which does nothing else than decision trees, which is pretty cool because it means that you can actually even read the output, achieves the best scores. With an F1 measure of 0.8 and an AUC, ergo area under the curve, of 0.867. And the major difference between these different approaches is really the way they look at text. So FactCheck uses dependency parse trees as well as significantly stricter rules when it comes to what the sentences should look like. And with that, it is basically able to outperform an approach which relies basically on a sequence model for sentences, which basically tells us that a little bit of syntax and semantics really goes a long way here. All right, those were the text-based approaches. We also have graph-based approaches to address this problem of fact-checking. So one claim in the campaign against Barack Obama really was that Barack Obama is a Muslim, which is incorrect. And the way we can use graphs to fact-check such things is one of the very first ideas was the idea of knowledge linker by Ciampaglia et al. And the idea here was simply to ask the following question: how related are the resources which occur in a claim? So if the resources are basically not related in a knowledge graph or are basically related by chance, then it is rather unlikely that that fact is correct. And what you can do is you can evaluate the most specific paths between resources to compute the score, a score tau, and then train a classifier to take binary decisions based on that scoring function. And if you train your classifier well with good training data, you'll be able to basically disambiguate between paths which occur by chance and paths which are likely to convey some important information. Yeah, and on the slide, you basically, apologies, I was a bit too quick here. On the slide, you basically see what you get if you use something like DBpedia. The connection between Barack Obama and Islam goes through Columbia University, Association of American Universities, goes to Canada, to Stephen Harper, Kilgary, Nadine Neshni, who studied in Kilgary, and then Islam. And as you can see, this path is very, very long, given that the graph has a diameter of 7. This is really basically as long as you can get. So fundamentally, there's very little evidence for the claim. So how does that work from a technical perspective. What knowledge linker does, it maps the knowledge graph to an undirected graph with components, V and E, of course, V being the vertices and E the edges. The vertices are the entities. So in the picture I showed you before, the Barack Obama and Stephen Harper's and so on. And there is going to be an edge if there exists a P which connects. So there's going to be an edge between V and W if there exists a P such that VPW belongs to the graph or WPV belongs to the graph. So fundamentally what it says is if two things are connected in my graph, in my knowledge graph, I'm just going to shove a link between them. So Barack Obama, alma mater, Columbia University will be transformed in an edge between Barack Obama and Columbia University. This obviously loses information by not considering the predicate itself. And the nodes are going to be declared adjacent if there's an edge which connects them, and they're obviously going to be connected if there's a sequence of edges which connects them. Simple graph theory, nothing particularly exciting here. Now, the way that the semantic proximity of two nodes is going to be defined is going to be via a path. And it's basically going to say that I can define what is called the semantic score, really, of a particular path, i.e. of a particular sequence of vertices, by taking 1 plus the sum I from 2 to n minus 1 of the log of the degree of the vertices. So basically what I do is if I have a chain of nodes, 1, 2, 3, and I basically have connections between them, I'm going to look at the degree of the nodes on the path between my V1 and my Vn, and I'm going to sum up the log of these degrees and then take the 1 plus the sum and take the inverse thereof, i.e. the more degrees you have between the two nodes, the less likely they are actually to be really related to each other. And the tau value is then going to be the max of all possible paths between V and W. So fundamentally what we're going to do is take the path which maximizes this score, the W score, and say, okay, that is the score which we assign to that particular path. And we can then use a classifier on top of that. We can obviously, there are alternative definitions here where you can take something like the max instead of taking the sum. That's basically then known as the widest bottleneck problem. But fundamentally, you take the degrees and you combine the degrees to get a score for the path. All right. Knowledge linker, it turns out the knowledge linker works okay, but because it neglects the predicates, it actually does not perform that well in practical applications. The algorithm knowledge streams, which is by Shiraka et al., came out in 2013, basically looks at the problem in a totally different way. And it basically maps fact checking to a flow problem. So basically what it says is, I want to find the optimal way to transform knowledge from here, from the source to the target, right? Given the graph in which I am. So I'm given the fact David and Goliath is a notable work of Malcolm Gladwell. And I basically say, which other ways would I have to derive this fact? And if I have tons of ways which have good scores, i.e. good flows, then I will say, okay, well, this is rather likely. Again, I'm going to skip up some of the technical details simply for the sake of time. But basically what it does is it says, given my input graph, which is G, which looks like this, I am going to create, first of all, a line graph. And the line graph does nothing else than taking the edges, for example, this A, and transforming them into nodes. So that A, so it takes this and connects that to that. And basically, it does the exact opposite with the nodes. So the B here, this B will be connected to this B over here, right? And then you can take this line graph and compress it. So the compressed line graph simply counts how many times do I have certain pairs of edges. Oh, so how many times do I have particular pairs of edges connected to each other? So you basically see that if you look at this AB2, you have AB here and AB here. So you can basically put the 2 here because of the evidence that you have. Let me just clean this up a little bit. So you have this evidence. Ta-da. You have this evidence and you have this evidence. So you can basically create this part of the compressed graph. And you can do that basically across the whole graph. You basically get a compressed line graph, which they call a label contracted line graph. And once you have that, you can basically then start computing on that particular graph by using flow equations. And the idea here is that the flow across edges is bounded. So there's always an upper bound as to how much information you can pass across an edge. The amount of flow which goes into a node must be equal to the amount of flow which goes out of the node, except for two nodes. The source node will have a positive flow because that's the source of your information, and the object node will basically have a negative flow in the sense of that's basically your sink, that's where everything goes into, and you basically simply solve then the corresponding flow equation on the line compressed line graph. Flow is bounded, that's pretty clear. Flow divergence basically is what I just told you with the negative and positive flows, as well as the zero for all the nodes which are not the source and the target. The capacity basically just reuses the equation from knowledge linker, which we talked about before. And yeah, when you do that, you can basically then have significantly more information because you basically reuse the predicates as to whether there's enough information to actually claim that the fact is true or not. I'll show you some evaluation results in a second. The approaches on corroborative paths, which is an approach from I think last year, 2019, is when we published that paper, actually goes a step further and basically says that the evidence for, let me clean this up, the evidence here for if questions such as is the nationality of Barack Obama US American will basically consist of a bunch of parts, and basically we want to use terminological knowledge to prove parts. And what we mean by terminological knowledge is really the ontology of the knowledge graph. We want to see, we basically say if we have a fact, we want corroborative evidence, but that corroborative evidence must abide by the semantics of the knowledge graph, which is something that was not considered in previous approaches. Now, it's going to be a bit technical, but I'm basically going to give you the fundamental ideas here. I'm not going to explain all the indices. You can obviously read it up. But what we do first here is define what we call a directed path. So when we write this pi k v0 vk, what we fundamentally mean is that it is a directed path of length k between v0 and vk. And you can then have an undirected path, which is basically an undirected path of length k between v0 and vk, and that basically is our paths. Those are paths in the knowledge graph, exactly like you would expect from knowledge graph theory. So a non-directed path between a directed path, my apologies, between Barack Obama and USA would be something like Barack Obama, birthplace Hawaii, Hawaii, country USA. You can also have an undirected path between Barack Obama and USA, where Barack Obama is an alumni of Greenwich High School and the country of Greenwich High School is USA. Pretty straightforward, nothing particularly fancy here. We, however, can go further and define typed paths. And a typed path is as follows. We'll say a typed path K, or the set of typed paths between the types Tx and Ty of length K are basically paths pi K, V0, Vk, such that gamma V0 basically tells you the different types that the resource V0 has. So the type of V0 must be subsumed by Tx, and the type of Vk must be subsumed by Ty. So for example, if you have the types person and place, you can say that pi2 txtk, so pi2 person place, will contain the path Barack Obama Party, Democratic Party, country USA, simply because Barack Obama is of type person and USA is of type place, right? So basically restrict the type of paths which we are allowed to put in this set by looking at ontological information at subsumption relations. Okay, let me clean this up and move on. Okay, now we can create what we call a Q-restricted type path. It is a type path, so you can see that this remains, but we add a further condition where we basically say that the predicate, the sequence of predicates in the paths must be of a certain type. So then it must fulfill a particular condition, and it is that it must be exactly the sequence which is defined in this vector. So you can basically have the Q restricted typed path between persons and places where the Q is birthplace country will give you exactly this guy as an instance of such a path between Barack Obama and USA. Once you have this, once you have basically restricted paths with respect to ontological information, you are going to say that only type paths between the domain and of P and the range of P, where P is this particular relation between SP and O, only these type of paths can corroborate SPO. So basically, fundamentally, what you're saying is that I'm only going to look at paths of a certain type to count evidence towards P, which is fundamentally what the other approaches did not consider or fail basically to integrate in their computation. And once you have that, the rest is actually pretty straightforward. You can define corroborative paths for a predicate as being basically the union of all the possible paths of length k which abide by the constraints of domains and range. And you can now define the association strength between a particular predicate P and a particular path. I'm not going to go through the equation. Fundamentally, what it tells you is you have to use the normalized pointwise mutual information, but you have to be careful in the way you compute it. So that's fundamentally the equation, but the way it's implemented is slightly different. And for the veracity calculation, i.e. for computing how likely a predicate is to hold between two things, you'll basically use 1 minus the product of 1 minus the MPMIs of the different paths across all the path evidence which you have found. So basically you're looking at the disjunction of these paths and asking how likely is it that this disjunction is true. Okay. Just a sec. I went too fast. And that approach is called Copal, and we compared it with PredPath and basically Knowledge Linker and similar approaches. And what one can basically show is that approaches such as KS basically perform relatively poorly. PredPath already performs quite well. It is basically derived from the approach which I showed you before with the flows, but you can still boost a little bit of the scores, especially when you start thinking about properties by another 1 to 2%. And actually, our current works show that you can go even a step further. We are going to hopefully present that next year. The experiments are running. But again, fundamentally, what this says is a little syntax and semantics really does go a long way. All right, and we get to the end of my talk as well as to the summary slides. So fundamentally, what I talked about today was fact-checking, how we do fact-checking, how we basically go from fact-checking text to fact-checking knowledge graphs with text to fact-checking knowledge graphs with themselves. And there were three main points that by looking at semantics, by doing a correct work in feature engineering, and by using embeddings, we are probably going to be able to be even better than what's available out there at the moment. But what's available out there is pretty good already. And there are quite a few interesting challenges coming our way, such as query synthesis, negative fact checking, and the automated extraction of features. That's it from my side. Thank you very much for listening. And obviously, this work was not done alone. This work was done with my collaborators, Michel Rudd and Zafat Ziad. There's more info on all of this at our project webpage, or at our webpage, which is diceresearch.org. And some of the key papers you can read to get more information are cited there. That's it. Thank you very much.
Merci beaucoup, Axel. Merci, Prof. C'est toujours un plaisir d'écouter tous ces travaux derniers calibre, on pourrait dire, dans le domaine. Alors, nous avons quelques questions sur le chat, dans le chat qu'on va prendre. Alors, la première question. Alors, merci, professeur.
Gisela, je ne t'entends plus. Je ne sais pas, je crois que tu es en mute là ou quelque chose. Je te vois, mais je ne t'entends pas. Je ne sais pas ce qui est arrivé là.
Allô, allô?
Yeah, maintenant on t'entend.
Ah, ok,
C'est bon.
super. Parfait. Donc, je disais merci au professeur pour la présentation. On va regarder quelques. Alors, on a des questions dans le chat, donc j'étais à ce niveau-là. J'ai eu des soucis tout à l'heure de connexion. Donc, la première question qui nous vient de Martial, qui nous dit, Pouleyer, qui nous dit, bon, merci professeur, ne serait-il pas possible de fabriquer des médicaments? Non, ça c'est pour, ah oui, ça c'est le slide précédent. C'était la présentation précédente. OK. Amadou, Mamadou, thank you for an interesting presentation. What is different between fact-checking and detecting true and false information? That's
The goal is basically the same. You have facts and you want to detect what is correct and what is incorrect. Now, when you say basically true and false information, generally you're looking at text as your source. So basically you're given a textual document and you're asked which of these sentences are correct and which of the sentences are not correct. Basically, you don't have formal semantics, you have natural language semantics behind natural language text. And in knowledge graphs, you have basically formal semantics, which means you can exploit those pieces of information pertaining to domain and range information, as well as subsumption relations to actually answer these questions in a more efficient manner.
Okay, great. Thank you. Je sais qu'il il a le chat s'il veut, s'il est d'accord, s'il a la réponse à la question. Alors, Iliassou Jayou nous demande, vous demande alors, je voulais savoir sur quel historique vous appuyez pour savoir si une information est vraie ou fausse. Et en fait, alors, il demande sur, alors, l'historique, après, sur l'historicité des données qui sont peut-être utilisées dans le.
Oui, en fait, ça dépend naturellement du genre de fait qu'on est en train d'essayer d'évaluer. Donc, si on prend des faits qui ont une véracité absolue, comme par exemple Einstein a eu le prix Nobel, en fait, on va regarder dans tous les documents possibles. On va regarder dans la base de données entière, quoi, ou bien le knowledge graph entier. Euh, Quand il s'agit de faire ce qu'on appelle temporal fact-checking, on essaie de savoir quand est-ce qu'un fait était vraiment valide. Par exemple, quand est-ce un joueur de foot particulier a joué dans une équipe. Là, on va regarder justement quand les articles ont été publiés. Ça devient un peu plus compliqué, mais il y a des papers sur ça qui font exactement ça. Par exemple, le paper de Gerber et al. 2015. Et ouais, en fait, Anis Arula a aussi publié quelque chose sur ça en 2019. C'est ce qu'on appelle volatile facts ou même volatile fact-checking. Et là, on regarde naturellement quand les données ont été publiées. On intègre ça comme source de données.
Ok, merci. Alors, j'avais deux petites questions. Alors, au niveau de la slide 23, lorsque tu présentais les méthodes basées sur le texte, alors je posais la question, je voulais savoir à peu près, est-ce que vous avez, en termes de l'état de l'art, est-ce que vous allez au-delà en termes de score sur la co-référence, par exemple? Parce qu'il y a cet aspect de voilà, Barack Obama, et tout ça. Est-ce que vous avez la possibilité de faire plus que ce qu'on voit un peu dans l'état de l'art ou bien vous utilisez ce qui existe déjà?
En fait, on utilise ce qui existe déjà. Donc, on fait de la co-reference resolution dans ce contexte. Vraiment, c'est juste un outil pour savoir où se trouvent les phrases qu'on veut utiliser pour en trouver de l'évidence pour les faits qu'on est en train d'essayer d'évaluer. Donc, les gens qui font la recherche dans le traitement automatique du langage font co-reference resolution et ainsi de suite. C'est juste un autre domaine de recherche. On utilise leurs résultats pour faire ce qu'on doit faire.
Exactement. Et après, comment, alors oui, c'est à la fin justement, j'avais posé un peu la question. Avant, c'était comment vous gérez la négation, c'est que ce soit implicite ou explicite dans les faits, en fait, sur les méthodes
OK.
basées.
Bon, c'est super intéressant. Il y a du travail dessus. Sur les gens qui font sentiment analysis, par exemple, ont fait beaucoup de recherches sur comment utiliser les features comme la négation pour en fait savoir si une évidence est positive ou négative. Donc, on peut réutiliser ça. En général, ils regardent le dependency path tree, donc en fait l'arbre de dépendance entre les différents éléments de la phrase, et ils disent tout ce qui accroché une négation va donc avoir un score négatif. Et avec ça, justement, on peut travailler avec les doubles négations et les triples négations pour donc avoir des scores sur l'arbre. Et c'est ce qu'on utilise dans la posteriori comme features, en fait, pour faire la classification des faits. Quand il s'agit de négation implicite, c'est beaucoup plus difficile. Mais ce qu'on peut faire, c'est qu'on essaie d'apprendre comment représenter les prédicats, donc comment représenter les relations entre sujet et objet. On peut justement utiliser du feature learning et justement, les gens plongent généralement les trucs comme les ressources et les prédicats sont en fait dans un espace vectoriel. Et dans cet espace vectoriel, on peut donc réserver une partie de l'espace pour des négations.
Ok. En fait, donc vous ne faites pas, il y en a des approches qui font juste ils essayent de faire de la normalisation de guillemets pour passer de, s'ils ont détecté la négation, à une version positive avant de, c'est-à-dire qu'ils font ça un peu comme un pré-processing avant de dans le graphe.
Mais en fait, c'est pas nécessaire, puisqu'on peut seulement représenter ça avec des features négatives. Et puis, ce qu'on fait, c'est qu'on apprend donc que quand on a trouvé des features négatives, c'est une négation. Donc, en fait, c'est vraiment l'opposé de ce qu'on est en train de chercher dans l'espace.
Okay. Another question then, congratulations, professor, presentation. Alors, with these stats of unverified information that can be found on Wikipedia, do you encourage its use as a reference?
Not for scientific publications, no, I do not. Because basically you're doing a lot of guesswork. Use reference publications. Or use something like Scholarpedia, which is basically also reference text, where people have double checked.
Great. Ken, Zebro Salifou, thanks for the presentation. It's hard to imagine the size of these knowledge graphs. So are they manually fed, or are there some tools like AI-based tools, for example, which automatically generate a knowledge graph node?
It really depends on the knowledge graph. So a knowledge graph like the Google Knowledge Graph, just to tell you something about sizes, you are usually talking about in the order of 10 to the 8, 10 to the 9 nodes, and basically you square that for the number of relations. So you're usually 1 to 2 order of magnitudes further than that if you think about the number of relations. So if you think about the DBpedia knowledge graph, for example, which is based on Wikipedia, you will have something like 4 to 5 million nodes, and the number of relations is going to be around 1 billion, or even a bit more than that. And these are very commonly extracted automatically from some sources. So DBpedia basically uses the info boxes in the Wikipedia pages, as well as some textual extractors to basically get the nodes and the edges. So those are the types of sizes, and pertaining to how they are gained, using some tools like AI-based tools. If you want to see one, you can go to, let me see here.
Okay, while you are looking at that, okay, the last question probably for this section: how is knowledge graph better than a classification model built with a text mining step?
Very simple. A knowledge graph has a semantic layer. So if you consider the evaluation results that we had with and without the semantic layer, by using the semantic information that you have in a knowledge graph, i.e. the ontology, you simply can have better restrictions on the evidence that you consider. And because you have better restrictions on that evidence, you also get better scores. Ergo, a knowledge graph basically provides a semantic layer which improves your results.
Great. Je crois que merci beaucoup, Axel. On va
c'est un plaisir.